Hello everybody, how y'all doing? Today we are going to be going over trigonometric substitution. And you're going to be thinking, what the hell is that? New way? Yes, there's a new way to integrate. And this new way is actually my least favorite way. But it is a useful way. It's not hard, it's just repetitive like usual. It's just we have a couple extra steps. Nothing too spicy. So let's start. Here, how do you integrate this? If you thought u sub, that would be right. Because when you set your u to your 4 minus x, and remember we said we set your u to the whatever that looks weird, that root, whatever under the root looks weird, so we're going to replace it with u. And now my du equals 2x dx, and then I can isolate, right? And now as you can see, this part right here takes over this part, and this part right here takes over this part, and that is good. Then what you'll get is, if I continue this here, I'll get the integral of 1 over u, the square root of u, du. And then what will happen here is the integral. If I rewrite this, I can get 1 over u, 1 over 2, that's the same thing. Not half 1u, but u to the 1, 2. There, I'll zoom in. That looks like an n when I zoom in, which is crazy. Alright, so what I'll get is 1 over u, 1 over 2, du. Now if I rewrite this again, I will get an integral of u negative 1 over 2 du. Now when I integrate this right here, oh my god, okay, right here, then I'll get the integral. So when I integrate this, I'll add 1, and so I'll get u to the 1/2 divided by my 1/2, and it's the same thing as saying u flip and multiply, right? And my plus c. And then I can replace my u with whatever I have, which is 2 times 4 minus x squared over 1/2 plus c. All right, and that's just a simple use of. Now, what happens if I don't have that x at the top, and I can't really replace this number at the top with my x right here? What can I do? And this is where trick comes into place. So if you remember our equations, we had sine squared x plus cos squared x equals 1. And then if we rearrange this, what we'll get is sine squared x equals 1 minus cos squared x. And we also say secant squared x, and this is given 1 plus tan squared x. And if we rearrange our tan, what we'll get is secant squared x minus 1. And if you can tell here, the difference is you have number minus trig, you have number plus trig, and then you have trig minus number. These are different combinations. And so what you'll do is you'll look at this and you'll be like, well, which combination is this? This is number minus variable. So where's number minus variable, or trig? You see this is trig minus variable, variable plus trig, number plus variable, and then 1 minus variable, number minus variable, same thing. And so what we'll say is then you make your x equal to this without the square. All right, you make your x equal to this without the square. And so we'll say is x equals my sine x. But here, a, what you put in a is your root 4. All right, and you'll see why we're doing this. But you want to take your root 4, or whatever the number here is, and you want to root it. So what I'll get is x equals 2 sine x, because I rooted this, which is 4. So, and that's what I'm placing as my 2. So now when I do the following, and this is, by the way, I apologize, this is not x, but this is theta. All right, and so now I have my dx equals 2. So if I integrate 2 cos theta d theta. Okay, now let's go up here and let's replace some stuff. So the integral 1 over root, before stays, we haven't replaced it, minus. Now I did say my x equals 2 sine, so 2 sine theta, and then obviously I have this square, and then my dx gets replaced with 2 cos theta d theta. All right, now what can we do? Let's apply the square in. Right? I'm just going to apply the square in, that's right here. And so I'll get 4 sine squared theta, right? And then I have my root. Oops, this is 2 cos theta d theta. And now when I integrate this, when I keep going, I can pull out a 4. And this whole idea is because you see here, you can't apply when you have the root of, like, let's say, you know, x squared minus x squared. You can't just, well, this you can minus it, but here let's make it so you can't minus it. X cubed. Oh my god, what's wrong with my writing today? X cubed. Right? You can't say this is root x squared minus x cubed. Or sorry, you can't say this minus the root of x cubed. You can't split it like this because they're adding. You see, but if they were multiplying, if we had x squared times y cubed and you square root this, I didn't do it x cubed because you're like, oh, you could add them together, so I want to take that argument out of the way. But let's say it's y like this, then you can say, okay, well, this is the same thing as x squared times the root of my y cubed, right? So what we're trying to eventually do is get these to multiply so we can root them. And so if we pull out a 4, if I pull out a 4, what I'll get is 1 minus sine squared theta 2 cos theta d theta, and I still have my root, don't forget. Right? Now what can I go from here? Let's see. I could root the 4 because now they're multiplying. You see, now they're multiplying, so I could root the 4 and root this separately. So if we want, we can say 1 over 2. This is going to be 2 root 1 minus sine squared theta. Right? 2 cos theta d theta. You see this cancels out with this now. All right. Now what can I do? I still can't root this because this is 1 minus sine squared. I still can't root this. So what I can say is I do know that my cos squared theta equals 1 minus sine squared theta, and that's perfect. So I can sub this in. So all I get is 1 over root cos squared theta. I'll have a cos theta d theta, right? And so you see now this, I'll put it in red. You see now this cancels out with this. And what I get is the integral of 1 over cos theta and then cos theta d theta. And you see now this cancels out with this. And I just got my integral of d theta, which just gives me theta plus c. Now, you can't leave it like this because we started the question in terms of x, so you have to turn this back in terms of x. How do you do this? If you remember, we had x equals this, right? So if I copy, paste this, drag it down. So if you remember, I had this. Whoops, I don't know why this didn't. Okay. I had this, right? And so what I can say, well, if I do x over 2 equals sine theta, then I can say sine inverse of x over 2 equals theta. So I can come here and be like, okay, so sine inverse 1 x over 2 plus c. And that would be my solution. All right, and that is how you integrate this. It's a couple of steps, pretty simple. You can make the connections. It's not that too bad. What have we done? Blah, blah, blah. I don't think I'm going to go through this because you can go on her notes and really see everything, what she wrote. It's like, why does this work? Pretty sure you guys don't care why this works. I'm not even going to go through it. We have some useful trig identities, and that's why we will rearrange this to equal our sine squared theta equals 1 minus cos squared theta, right? That was our first one. And here, this is one of them already. All you got to do is keep your tan. So I'm going to keep my tan. And I'm going to say take the one on the other side. And that is my 3 identities, right? This is 1, 2, and 3. You will never, okay, side note, you will never be doing this. You will never be using this identity, all right? we're just going to be using this one because this is the same as this one. All right, it's the same thing. So we're only going to be using this one. But you see here is different because this is +1, this is -1. But this is, both of them is 1 minus your variable, 1 minus your variable. So this is the only one we'll be using. All right. Now, so what this says is if the expression is this, what do you choose? Variable minus, so you see, number minus my cos. And what is your x? What would you set your x as? And you see, we set our x as the left of the equal. So equals our a, which is your root. So you see right here, your root cancels out with the squared. So you get a. So if this was a 9, you would do √9, right? Because we want to undo the square, because then we're going to redo the square because of this one right here. And it will get us our a, and then that kind of works out. So all you got to do, remember, is that your a is the root of whatever your a is here. And so this would be sine x. This is plus, so plus tan theta, and then we set squared, and then we set our x to the whatever's on the equal sign, which is secant. A secant theta. This right here is supposed to be theta as well. And this is secant squared theta minus 1. I'm just looking at, you see this is variable minus your number, variable minus my number. And this is actually, it wouldn't be, yeah, actually no, it would be 1 because we're substituting this in, right? So, and then x equals a, the equal sign, which is tan x or theta. All right. Now these are some trig, and these are givens. So are you going to be using these? Probably. Should you know them by heart? Yes. Saves you time. So now we are going to the next integral. And it's like, well, okay, what can we do with this? So we have 1 minus x squared. What is 1 minus x squared? You see, as soon as you see that 1 at the top, you know you can't really use sub anything because your dx will always have some x in it. And so you can't really replace it. So right away you go like, oh, okay, this is a trig, substitution. So we have 1 minus, we have sine squared x equals 1 minus our cos, right? And that's 1 minus, that's 1 minus. Therefore, my x equals, we said the left side of the equal, which is sine. And then what is my a? It's the root of 1, which is just 1, so I'm not going to write it. All right, and my dx equals, and this is, again, keep making the same mistake here. This is theta. All right, and so this is theta. Now dx will be cos, oh my god, horrible looking theta. D theta. Now let's go on this side and start replacing stuff. Our x is sine. Don't forget your squared. And then my root is 1 minus, what do I have? Sine? Right? Whoops. Yeah, so sine theta, all squared. And this is all over 1, of course. If I just make this look a little bit better. There we go. And my dx is cos. Right? Now, what can I do here? Right? What can I do here so what I'm going to do is, the first thing I'm going to do is simplify a little bit. How can I simplify? So 1 over, yeah, so I'm just going to get rid of, to be honest, it's not even simplifying. So I'm just going to get rid of my brackets. So it looks recognizable. You see I applied my square on the sine. Right? Now, what is this? 1 minus sine. That's the same thing as saying cos squared theta equals 1 minus sine squared theta. Right? That's the same thing. So I have the integral of 1 over, and this is squared, right? So you'll get sine squared theta. I'll just copy this from the top. My root, I'll get root cos squared theta. And as you can see here, this cancels out with this. Here I still have my cos theta. You see, if I rewrite this, I'll get the integral of 1 over sine squared theta cos theta and d theta. And as you can see, this cos cancels out with this cos, and what I'll get is the integral of 1 over sine squared theta. Now, can I integrate this? No, I can't. So what I can say is 1 over sine squared is the same thing as my cosecant. Right? This is the same thing. But since this is squared, this is cosecant squared. D theta. Right? And so what is the integral of your cosecant squared? You go up to your table. We go up to our table. We can see where is a cosecant. There you go. See, we have cosecant squared equals cotangent. So the derivative of cotangent is cosecant. That means the integral of cosecant is cotangent, right? You go back in reverse. And so if we go here, we have positive, but we know that this is negative. So what we're going to do is we're going to apply the negative, right? And so when we have it is we're going to have negative cotangent theta plus c. And now I got to obviously replace my theta. So I'm going to go to my x, and my x equals sine theta, which is the same thing as saying sine inverse x equals theta. So I'm going to take this, come here, negative cotangent sine inverse x plus c. And that's about it. And so we have some more examples. We have a lot more examples. I'm trying to see which one I do want to go through. So you see, this one is the same thing that we did upstairs, just different identity. I don't know why I said upstairs, but the same one we just did earlier, different identity. This is a plus instead of a minus. Here, this is a u sub, because, right? So, see, u equals, you didn't catch that, you should have. This is our x to the top. So you see, I have x squared minus 9. My du equals 2x dx. Right? And now what I'll have is I have this, replace this like we said earlier, and I have this, replace this whole thing. And so what I'll get is the integral of 1 over root u dx, d over 2. And then from here, you could keep going and solve the rest. So I'm going to leave that. Here, what do I have here? Here you could also use a trig. Now this isn't a 1 over, which is fine. This is a good example to go over. I'll go over it. Let me just check the above one. This one is the same as the ones we've been doing above. It's just flipped. So you have your division the other way. But the way you do it is the exact same way. Right, so I'm going to leave it for you guys to solve that one. But this one, there's a little bit of difference, so I'm going to go through it. Alright, so this one is number minus variable, but my variable has a number within it. So what can I do to make this in a format that is more familiar to us, where we had a number minus a variable? Something like this, where I don't have another number here. So you see, if I actually gave you, I'm gonna write this in blue. If I gave you 25 minus 4x squared, I told you take out a 4, then you'd be able to take out a 4, and what you'll do is you'll do 25 divided by 4 minus 4 divided by 4. That's how you take out a 4, right? And then you get these two cancel out. If this was divisible, then you would take it out. But here, it's not, and so you're going to leave it, right? And so what we'll get is 4 times 25 over 4 minus x squared, right? And this is technically a variable. It is a fraction. It looks ugly, but it's a variable, right? And so that is one way to do it. And if you guys don't get it because of the division, I'll give you something that doesn't divide. Let's see, what do we have? If I go 4 minus 2x squared, until you take out a 2, so you'll have 2 minus x squared, right? And so we can do this the same thing here. So I'll do the integral. I'll just simplify. So I'll keep my root. I'm going to pull out a 4, so I'll get 4, 25 over 4 minus x squared. And you see, now this is in a format that I can understand, that I've dealt with, and it makes it a little easier. And so you see, now we can do like we've always been doing, where now this isn't a divide by 1, which is fine. You could still use the trig sub here. And so we know our sine squared x equals 1 minus cos. And this is for the 10th time. This is a theta. Okay, and so you see now, this is number minus variable, and this is number minus variable, which is great. So now then we set our x to the left side, which equals, what do we equal it as? Or 2. Remember, we want to do the root of my variable here. Okay, so here, actually, I'm going to start here and rewrite this. Since this is multiplying, you can apply the root to the 4 and apply the root to the bracket. So root 4 is 2, right? So the integral would be 2. And then root 25 over 4 minus x squared. Right, now I can take out my 2. And now this is an even more simplified form. All right, now my x equals, I have to, this is my a, and remember I told you square root your a, so this is the square root of my a, which is 25 over 4, right? And then minus, or sorry, not minus, sine theta, which is the left of my equals. And now if I were to simplify this, what I'll get is 5 over 2 sine theta, and now I gotta get my dx, which is 5 over 2 cos theta d theta. Now just replace things. This is the easy part, right? I get 2 the integral square root 25 over 4 minus 5 over 2, right? And then I have sine, well, not squared, sine theta. All this is squared because of my square here, right? And my dx is 5 over 2 cos theta d theta. Now what I can do here, if I zoom in a little bit more, what can I do here? Let me apply my square. So I'll get 25 over 4 minus 25 over 4. All I did was apply my square to the 5 over 2, which is 25 over 4. And then I get sine squared theta. And as you can see now, we're back to where we've been, always doing the same thing. It's pretty repetitive, I'd say. So you see now, integral, I can pull out 25. So now I have a root 25 over 4 bracket 1 minus. And now we are right at where we want to be. And this would be 5 over 2 cos theta d theta. Right? 1 minus sine squared is cos. So this is 2. Since this is multiplied, I could root this, which I'll get this times the integral of 5 over 2. I just applied my root to the 25. I solve my root. I'm going to replace 1 minus sine squared with my identity, which says cos squared theta equals 1 minus sine squared theta. I'm going to place this here, so I'll get cos squared theta times 5 over 2 cos theta d theta. Now what can I do here? This whole thing is multiplying each other, right? You have this times this times this times this and times this. And so I can combine these together and multiply them. So I'll get 2 integral 5 times 5 is 25. 2 times 2 is 4. Right? Now I still have my square root, but this square root cancels out with my 2. So now what do I get? I just get a cos. And I also have a cos here. D theta. Right? Now I can take my 25 over 4 out. So because it's constant. And I can square root these. Sorry, not square root, just square. So this will be 2 times 25, which is 50. So this is 50 over 4 now. And then I'm going to do the integral of cos squared theta. Cos times cos is just cos squared. Right? Nothing too special, nothing too crazy. Now, remember when we said when you have a cos squared or a sine squared, you can't use sub this, you can't really integrate. I could change this into the identity that says, you know, sine squared, I would say cos squared theta equals 1 minus sine squared theta, but I'll still have my sine squared here, and I can't really integrate that either. So what I can use is half angle, because remember, cos squared theta equals 1/2 times 1 plus cos squared theta. Did I remember this correctly? Let's see if we have half angle formulas. I don't think I have them on this page, but you guys can double check the half angle. I'm pretty sure that is the right answer, so I'm just going to go ahead with it. If I am wrong, I apologize. Alright, but I'm never wrong, so too bad. Now, what I'm going to do is substitute this. So I still get my 50/4 integral. My cos squared becomes 1/2. 1 plus, and this is not squared. This is 2. Right? And so 2 theta, d theta. Now if I keep going right here, I'll get again 50/4. I'll expand this. Alright, so I'll get the integral of 1/2, because 1/2 times 1 is 1/2, plus 1/2 times cos is just 1/2 cos 2 theta and d theta. Right? Now 1/2 can come out, right? 1/2 can come out. And so what I'll have, actually here, I'll go to the bottom here. I'll just separate this. Alright, and so what I'll get is, I'll take my 1/2, well actually no, I can't take my 1/2 because this is adding, so I do have to integrate this. So now I can actually integrate this. I get 50/4 times, right? Now the integral of 1/2 is 1/2 theta plus the integral of 1/2 cos 2 theta. 1/2 stays. The integral of my cos theta is, I believe, negative sign. Again, if I'm wrong, my bad. Negative 1/2 sine 2 theta. But remember, when you do sine 2 theta, you have to divide this by the derivative of whatever's inside here. So the derivative of 2 theta is just 2. And so if we divide by 2, this turns into a 4. Right? Because I would have 1/2 times sine theta divided by 2. And this is just 1/4 times sine. Okay? So what I'll get here is 1/4 sine 2 theta. And all plus c. And now if I expand this out, what will I get is 50 over, so 4 times 2 is 6 theta minus 50 over 16, because 4 times 4 is 16, sine 2 theta plus c. Now don't forget, what is my theta? My theta in this case is, what's my x? This is my x. So my theta, if I were to isolate for theta here, I will get x divided by 5/2 equals sine theta. Now this is, I can flip and multiply, right? So I'll get 2x over 5 equals sine theta. Now I can do sine inverse of 2x over 5 equals theta, right? And now what I'm going to do is I'm going to come down here and just substitute. So what I'll get is 50/6, and my times sine inverse 2x over 5, and that's my theta, right? Minus 50/60. I'm not sure if you can simplify these into a more simplified fractions, but do check that. And then I'll have this times sine, and then 2, and then my theta, which is sine inverse 1. I know this is messy, but it's not too bad, since you just got to keep track of what you're substituting in. Here you can make small mistakes, and if you do, I don't think you lose too many marks, as long as you know the general path you're going in. Like, you could forget maybe a 2, you could forget, you know, a division, and the teacher will probably know, whoever's marking knows you know what you're doing. Is just, you know, sometimes you're anxious on a test and you forget little things. So you lose like 0.5 a mark. If you pay extra attention, you shouldn't lose any marks, but you just gotta remember the small details, like don't forget to get your theta and sub it in. And that's how you solve this one. It's a little bit lengthy, just because we used a half angle, but usually it's not too bad. It's the same process. And this is the same process again. It's just different identity. Recall, when working with definite integrals, performing a substitution, you have two options. So the above question could be done in a different way. Oh, because of this. So performing, when you do this, if you keep it, if you turn everything in terms of x, you know how when we went up here, we turned everything in terms of x, then you will plug your integral in normally, because this integral bounds are in terms of x. But if you're, you see up here, where is it? Yeah, right here. You see right here, my integral is I turned it in terms of theta, and so my bounds, if they were like in terms of x, like 1 over root 3, like we saw below, what you'll do is you can take your 1, substitute it into your x, and solve for your theta. So I can take this 1, substitute into my x here, solve it, sine inverse of, so 1, 2 times 1, so you get sine inverse of 2 over 5, right? And that would give you your theta. Now your new bound becomes whatever answer you got for your theta. Then you do the same thing for your bottom bound. You take this and you plug it in, so you'll get, sine inverse of 2 times 1 over root 3 all over 5 equals theta. You plug this into your calculator, you'll get some number equals theta, and that would be your bottom bound. And so once, so you see how it's in terms of theta here? You'll get whatever answer here in terms of your bound, right? And then when you solve and you get this equation, your plus c, you don't have to turn it back in terms of x. You can just sub in your new bounds now, because they're in terms of theta. And so you can just put them in terms of theta, and then you can plug everything in your calculator and get whatever answer you get. And so that's what they're trying to say here, is that you can either convert the bounds in terms of your new integral, which is in terms of theta, or you, you work with indefinite, we know this one, or you turn the whole question, you see how we had in terms of theta? You turn the whole question back in terms of x, like we did here, when we isolated for theta and plugged it in. And that is the other way you can do it. So, depends whatever you're comfortable with. I usually do it this way, but you can also do it where you turn your bounds in terms of your new variable.